The air purifier industry earns billions every year. In 1989, NASA grew 3 houseplants that removed up to 96% of indoor toxins in a sealed chamber: peace lily, spider plant, Boston Fern. Over 10 years, they cost $950 versus $1,466 for a mechanical purifier. $5 million in lobbying later, not a single building code mentions them. The reason starts with one NASA scientist. At NASA's John C. Stennis Space Center in 1989, Dr. B.C. Wolverton led a team with an unusual assignment: find a way to clean the air inside sealed environments, like future space habitats, using nothing more than living plants. The team built airtight acrylic chambers, each just 0.152 cubic meters in volume, barely the size of a large suitcase. Inside, they placed potted houseplants and introduced measured amounts of 3 common indoor pollutants: benzene, formaldehyde, and trichloroethylene. The chambers were kept at around 25 degrees Celsius, with humidity allowed to fluctuate naturally. Over a 24-hour period, the researchers tracked about how much of each chemical disappeared from the air. The results were striking. The peace lily, Spathiphyllum monoloa, removed 79% of benzene, 89% of formaldehyde, and 23% of trichloroethylene from the chamber air. The spider plant, Chlorophytum comosum, achieved 96% removal of benzene, 79% of formaldehyde, and 65% of TCE. Boston Fern, Nephrolepis exaltata, showed strong performance as well: 73% benzene, 61% formaldehyde, and 70% TCE removed in just one day. These numbers were not isolated outliers. Each test was run in triplicate, with consistent results across the board. NASA's memorandum concluded that these plants, along with their root microbes and potting soil, could play a major role in removing organic chemicals from indoor air. The data were so convincing that by 1993, NASA issued a simple guideline: 1 medium-sized plant for every 100 square feet of space. For a typical home, that meant about 15 plants. The findings offered a low-cost, low-maintenance alternative to mechanical air purifiers, which rely on expensive filters and steady electricity. Yet the experiments had a catch. All results came from sealed chambers, far more airtight than any real home. The next challenge would be to test whether these dramatic removal rates could hold up under everyday living conditions. Plants like peace lily, spider plant, and Boston Fern do far more than just sit in a pot. Each is part of a living filtration system, drawing polluted air in through their leaves and roots. At the surface of every leaf, tiny pores called stomata open and close throughout the day. When a molecule of benzene or formaldehyde drifts into one of these openings, specialized enzymes inside the plant's cells can break it down, turning a toxic gas into harmless byproducts. The waxy outer cuticle of the leaf also acts as a sticky landing pad, trapping nonpolar compounds like trichloroethylene before they can even enter the plant. But the real work often happens below the surface. As plants draw water up from the soil, their roots exhale moisture, gently raising the humidity in the room by 3 to 5%, a side effect that helps dissolve more VOCs into the air, making them easier for the plant to absorb. Around the roots, a dense community of microbes thrives in the potting mix. These bacteria and fungi don't just live off the plant's leftovers, they actually help finish the job, breaking down VOCs that pass through the roots and converting them into carbon dioxide, water, and simple nutrients. This partnership between leaf, root, and microbe is what made NASA's chamber experiments so effective. Yet in real homes, open windows and HVAC systems constantly bring in fresh air and dilute pollutants, making it harder for any single plant to keep up. The next step would be to see if these biological pathways could deliver the same results in a typical living space, outside the tightly controlled world of laboratory chambers. In 2014, a team of horticultural scientists set out to test the spider plant's reputation as a natural air cleaner under conditions closer to everyday life. They selected a sealed room of 15 cubic meters, about the size of a small bedroom, and introduced formaldehyde at an initial concentration of 10 parts per million. This level is far higher than what's typically found in homes, but it allowed for precise measurement of changes over time. One healthy spider plant was placed at the center of the room, and air samples were taken at regular intervals using high-performance liquid chromatography to track the formaldehyde concentration. By the end of 24 hours, the results were dramatic. Formaldehyde levels had dropped by 95%. The researchers repeated the experiment in triplicate, confirming that the effect was consistent. Controls with no plant in the room showed only minor decreases, indicating that the spider plant itself was responsible for the vast majority of the chemical removal. Temperature and humidity were kept within typical indoor ranges to ensure the plant's normal physiological function. This study has been widely cited as proof that spider plants can rival or even outperform mechanical air purifiers, at least in a tightly sealed space with an unusually high pollutant load. However, the experiment's design raises important questions about how these findings translate to real homes. In most residences, ventilation and air exchange happen constantly, and formaldehyde concentrations are much lower, typically between 0.1 and 0.5 parts per million. Under those conditions, the same plant would likely achieve a much smaller percentage reduction, as fresh air and lower pollutant levels slow the rate of removal. The 2014 replication added valuable evidence that plants like the spider plant are capable of significant VOC uptake in controlled environments. Yet it also highlighted the challenge of matching laboratory results to the complexity of real-world living spaces, setting the stage for a closer look at the practical realities of plant-based air cleaning. EPA data shows indoor air often holds 2 to 5 times more volatile organic compounds than outside, with formaldehyde and benzene among the most common. Most homes exchange air at just 0.3 to 0.5 air changes per hour, a rate that slows the removal of pollutants and limits what even the hardiest houseplant can achieve. NASA's original formula, 1 plant per 100 square feet, translates to about 15 plants for a typical home, but the numbers don't hold up. To match the minimum 0.3 ACH standard in a 1,500 square foot house, nearly 100 plants would be needed. Over 10 years, following NASA's plant plan costs about $950, including soil, pots, and replacements. A HEPA plus carbon purifier covering the same area totals around $1,466 with filters and electricity. Plants require no power and create only compostable waste, while purifiers need steady energy and produce landfill-bound filters. Yet mechanical systems remove pollutants far more efficiently, especially in homes with limited ventilation. The promise of plant-based cleaning shrinks under real-world constraints. Mechanical air purifiers dominate both the market and the regulatory conversation around indoor air quality in the United States. The Air Quality Products Association, representing leading brands like Dyson, Honeywell, and Blueair, has reported more than $5 million in lobbying expenditures over the past decade. Their efforts target agencies such as the EPA and the Consumer Product Safety Commission, aiming to ensure that mechanical filtration remains the only officially recognized method for removing indoor pollutants. Building codes and standards reflect this influence. ASHRAE 62.1, the nation's primary ventilation standard, specifies minimum outdoor air rates and certified filter requirements, but makes no mention of houseplants as a viable option. The International Residential Code and state-level regulations follow suit, focusing exclusively on mechanical solutions. No formal pathway exists for plant-based air cleaning to be recognized under current codes. EPA consumer guides and product certification programs list only devices that meet mechanical or electronic filtration benchmarks. In this environment, plant-based strategies remain sidelined, not because of scientific refutation, but because the rules have been shaped by industry priorities and a lack of large-scale, peer-reviewed field data. The gulf between NASA's promising laboratory results and official policy is widened by these economic pressures, leaving consumers with little guidance on whether a peace lily or spider plant can play a meaningful role in their home's air quality. In Ohio, a family set out 3 common houseplants: peace lily, spider plant, Boston Fern. After 3 months, their VOC meter showed benzene levels down by 25%, but the difference felt subtle, and the air purifier stayed on. In Portland, 2 spider plants and a peace lily brought a 22% drop in formaldehyde and eased nighttime coughing, though the improvement was less than expected. On a Texas ranch, a Boston Fern near the mudroom cut acetone by 42%, but only with careful watering and placement. These stories reveal measurable, if modest, reductions, 25, 22, and 42%, yet also the limits of plants in real homes. Meanwhile, over 200 scientific articles cite the 2014 spider plant study, most repeating headline numbers without new field data. More than half of these citations appear in reviews or summaries, rarely questioning the original findings. The numbers from Ohio, Portland, and Texas offer a grounded counterpoint to the echo chamber of academic repetition. Today, Americans spend over $4 billion a year on air purifiers, while the EPA still lists indoor VOCs as a major health concern. Yet NASA's findings, 1 peace lily, spider plant, or Boston Fern per 100 square feet, remain largely ignored. Sometimes the simplest solutions get buried in plain sight.